This demonstration is about another application of the pigeonhole principle. So the idea here, we've got the numbers 1 up to 32, and then we've got some set U, so set U of size 8, which is a subset of this the numbers 1 up to 32. And the claim is that we can always choose two different disjoint subsets A and B, such as the sum of the elements in A is equal to the sum of the elements in B, two different subsets of U. So let's try that. So here we're going to choose two. We've chosen the subset U, and now we're going to look for these subsets A and B. So in the first instance, we find this set A is 9, 22, 30, and B is 1, 12, 23, 25, and and these are as required. That's they're disjoint, and the sum of the numbers in A is 9 plus 22 plus 30, which is 61. And the sum of the numbers in B, 1 plus 12 plus 23 plus 25, that's also equal to 61. So let's try it again. Choose a different set U, and we'll try and find the subsets A and B. So this time you've got the set A is 8 and 28, and B is 1, 8, 11, 16. So this time these are different subsets, but they're not disjoint. Their intersection is 8. But they do have the same sum. We add up numbers in A, 8 and 28 is 36. And similarly, the numbers in B, 1 plus 8 plus 11 plus 16, that's also 36. But if we want to get a disjoint example, that's easy enough to do. We just take this intersection, A intersect B, which just consists of 8, and we throw out the 8 from A, and we throw out the 8 from B. So that just leaves... so A just becomes the set 28, and B becomes the set 1, 11, 16. So these sets are now disjoint, and the sum of the elements in B, 1 plus 11 plus 16, is 28, and that's also the sum of the elements in A, just because there's only one element in A, the sum is 28. And we can try another set U. Okay, and here again we find the set A is 1, 15, 17, 21, and B is 7, 17, 30. Sum of both of these sets is 54, and they have an intersection in this case. A intersect B consists of 17, but we can get rid of that. We just throw out the 17, and so A becomes 1, 15, 21, and B becomes 7, 30. Okay, and so now the sum of the elements in A is 37, and that's the same as the sum of the elements in B, and A and B are now disjoint. And we could try it some more times if we want. It would always work out. So now can we explain why that is? Here. So the explanation is like this. So we had a set U of size 8, and so if we look at all the subsets of U, the number of possible subsets is 2 to the power 8, which is 256. So we can call these subsets x1 up to x256. And we let Si be the sum of the numbers in the set Xi. So what range could that be in? Well, of course, Xi could be empty, in which case the sum would be 0. But more interestingly, what's the maximum it can possibly be? Well, so Xi is a set. It's a subset of our set U of size 8. So Xi has size at most 8. And the numbers in Xi, they're taken from 1 up to 32. So the biggest possible sum would be what we get if we just take the 8 largest numbers here. The 8 largest numbers here, 25, 26, 27, 28, 29, 30, 31, 32. So we can work out the sum of all those, either just working it out or using the arithmetic progression formula if you want. Either way, we get 228. So now we had these 256 numbers Si, and they're in the range from 0 up to 228, which so this set here has only 229 elements in. So the 256 numbers Si, they can't all be different. So we can find some pair of indices, I less than j, with Si equal to Sj. And then the two corresponding sets, Xi, which we'll call A, and Xj, which we'll call B. They're different, because I is different from j, but they have the same sum, because Si equals Sj. And they're probably not disjoint, at least maybe not disjoint, but if we want to make them disjoint, all we have to do is remove the intersection from A to get this set A prime, remove the intersection from B to get the set B prime, and it's easy enough to see that the sum of the elements in A prime is going to be equal to the sum of the elements in B prime still, and now A prime and B prime are disjoint.